Okay, so what we're going to look at here is we're going to calculate some two-sample t-tests. And in Excel, there are some built-in functions that we can calculate two-sample t-tests from when we have the raw data. But when we don't have the raw data, we actually have to use the formulas. And so in this video, what we're going to do is we're going to look at how to calculate the two-sample t-test from the summary statistics, where we have to actually use all of the formulas because we can't use the built-in ones because we don't have the original data. Now, the formulas for the two-sample t-test are going to differ slightly depending on whether you're using pooled or unpooled data. And so we're going to look at, in this particular video, we're going to look at calculating the unpooled two-sample t-test. So the unpooled test is not going to assume that the variances are equal. Whereas in the pooled test, which we'll do in another video, that test assumes that the variances are at least approximately equal. All right, so let us look at our question. So within a school district, students were randomly assigned to two math teachers, Smith and Jones, different size groups. At the end of the year, each took the same test. Now, in this case, because they're taking the same test, one might assume that the variances should in fact be equal. But it is an assumption that you're making when you make that claim. It's not necessarily a bad assumption, but it is an assumption. The unpooled test simply won't make that assumption. And they have a particular average with a particular standard deviation for one class and a different average with a different standard deviation for the other. And so we want to test the hypothesis that our two instructors are both equally effective. And we're going to use a 10% significance level. This one is higher than what we normally use, but that's mostly because it's not really that important that there is a distinction between them. And so if there is a distinction between them, that's it's not earth-shattering. All right, so first thing that we want to do is we want to set up our hypothesis tests. We want to state our null and alternative. Our null hypothesis is that mean 1 is equal to mean 2, and the alternative is that if they're equally effective, we're not saying who is better or worse. We're not saying that Mrs. Smith is better than Mr. Jones. That would involve a unidirectional inequality, less than or greater than, then we would have to worry about that. But in this case, we are just saying we're testing whether they are equally effective, which is essentially, are they the same or different? So we're not particularly concerned with whether Smith is better than Jones or Jones is better than Smith. We just want to know if they're different. So these are our alternatives, our null and our alternative hypothesis. Our test statistic. Now there are more complicated versions of this formula. When you assume that they're equal and there's no difference between them, then the difference of the means in your null hypothesis is 0. And so that portion of the formula cancels out. And so we're ending up with this. Should be a t-test statistic. And then the unpooled standard deviation for our standard error for our problem is the square root. It's the basically the weighted variances squared under the square root. Now, what makes our problem particularly complicated in the unpooled case is that there isn't an obvious way to calculate just from looking at the data what the degrees of freedom is for our test statistic. And so the formula, in fact, is extremely complicated for calculating that test statistic. So we're gonna go through that calculation, and we're gonna go through it in just a couple of steps at a time as we assemble this formula, so that we can find our degrees of freedom. It might be a fraction, it might be a decimal value, which is unusual in almost all the cases that we've seen in statistics so far. It's an integer, but in this case, it can in fact be a decimal, and it will just depend on the various variances and how things work out. Included in here is how we get to the variances. Since we don't have the original data, we're not going to calculate it this way. They're given to us, but we can use that to find, we're basically going to square our standard deviations in order to get these values. So these don't particularly concern us. All right, now what we want to know is who is the better teacher, or if there is any difference at all. So let's go to Excel and actually do these calculations. I've already copied the formulas over there, so we have them as our reference. All right, so here's our formula, our problem, so that we can get our information out of it, and here's our formulas. So what we're going to do now is we're going to start setting up our calculations. We're going to build a table and then extract our information from our problem, and then begin to calculate these formulas. All right, so mean 1 is our X bar 1 in our formula, and that was an 85. S1, and since the formulas all require S1 squared, I'm going to just, instead of putting S1, I'm just going to put S1 squared. That is going to be 15 squared, because the standard deviation is 15 and the variance is the square of that. And then we need N1, which is the sample size for the Smith group, which is 30. And then we need mean 2. That's our X bar 2. And that is 78. And we need S2 squared. That is 10 squared. And then finally, we need N2, which is 25. Okay, so those are our input values. And so now what we want to do is we want to start calculating our test statistic. So what I'm going to start by doing is I'm going to start by calculating this denominator, S1 squared over N1 is going to be this divided by that. And S2 squared over N2 is going to be, oops, I forgot to put my equal sign. Let me fix that. Is going to be equal to S2 squared over N2. And then my standard error is going to be the square root of S1 squared over N1 plus S2 squared over N2. That's just this denominator right here. And then if we were calculating a confidence interval in this context, we would need the standard error formula. And then we need to calculate our test statistic, which is going to be the difference between mean 1 and mean 2 divided by the standard error that we just calculated. So it's 2.06. All right, so then finally we need the degrees of freedom calculation before we can do our p-value. Now, the numerator, you'll notice, is the same as our standard error, except instead of taking the square root of it, we've squared it. So first things first, we're going to take our numerator of the degrees of freedom. And so that's going to be our S1 squared over N1 plus S2 squared over N2. And instead of square rooting it, we're going to square it. And then in the denominator of our DF formula, we're going to have S1 squared over N1 S1 squared over N1 squared divided by N1 minus 1 plus S2 squared over N2, S2 squared over N2 squared divided by N2 minus 1. Okay, so S1 squared over N1 squared, N minus 1, S2 squared over N2 squared, N1 minus N2 minus 1. Okay. There's no square roots or squares over the whole thing. It's just that. And then the degrees of freedom is then going to be that numerator divided by that denominator. So that's our degrees of freedom. So now we can go ahead and we can calculate our test statistic, we have our test statistic, our p-value. So the p-value, now this is a two-tailed test, so that's what we're going to use. T.dist.2t. And the x value is our test statistic. And the degrees of freedom is the degrees of freedom thing that we just calculated. And we're going to get 0.44. That is less than, now remember our significance level in this problem is a 0.10 rather, sorry. It's less than 0.10. Even if this was 0.05, which is the standard level, this would still be less than that significance level. And so we would reject the null hypothesis. The null hypothesis, if you recall, was that the two means are equal. So this is sufficient evidence to think that the two teachers are not equally effective, that they are different. Now, if you look at the scores, this would imply that Ms. Smith is actually the better teacher because her mean is higher. Now, you can't tell that just by looking at the means, but after doing the test statistic, we conclude that they're different. And so it then follows that since her scores are higher than his scores, that in fact, that does imply that she is better, more effective than he is. Okay.